Join audio, manage participants. Let's close that program. Okay, get my tablet connected. There, close that. Zoom on the tablet, my meetings, start meeting. Okay, continue. Now, disconnect the audio there. All right, everyone. So I am on over the weekend. I learned how to turn on the virtual background feature, except that for some reason, because the background in my room is not uniform, it can't tell the difference between my face, my bookshelf, some of the things in the background, parts of my glasses. Sometimes when I turn my head, parts of my face turn into Kraken Mare, which is one of the great methane lakes of Titan. If you don't know about that, it's one of the awesomest things in science. Saturn's moon Titan has liquid and lakes and rain. It's just that instead of the liquid being water, it is methane. All right, I think I'm gonna turn that off if I can find my settings to do so. Well, I'll just stop the video and share my screen. Okay, first, like I said, nothing will ever stop me from talking about books. We're going to be starting to talk about why it is that these integrals of exponentials keep showing up in optics. And we're going to be doing a much simpler version of it. But if you really want to learn about why these integrals of complex exponentials show up in optics, I like this book, Intro to Fourier Optics by Goodman. I studied from it when I was a sophomore. It's more advanced than this, but it's quite manageable. And it is really the Bible of Fourier optics. I got a used edition for $10 about several years ago. This hardcover is obviously more expensive. It's the newest edition, but you can find used versions of the old editions. And it really goes into why these integrals of complex exponentials matter. Okay, so we're going to be talking about diffraction. We're going to be talking about the fact that when light, a wave, hits an aperture, it spreads out in all directions from each and every point on the aperture. Before, we just talked about interference between 2 points. We talked about 2 points that are so small that, two slits that are so small that the path from one point on a slit is the same, the distance along one path from a point on a slit is the same as the distance from another point on that same slit. But now the slit is large, okay? And because the slit is large, the distance from here to there could be very different than the distance from here to there. And when people do the experiment, they find that if you send light through, you get a bright spot in the middle, which this time is not surprising, because this time, well, we've got an opening. Of course, there should be a bright spot in the middle, but there is this periodic arrangement of side lobes. And furthermore, people find that if they take the same aperture and illuminate it with different wavelengths of light, then longer wavelengths produce slightly wider and slightly more widely spaced spots. But on the other hand, if you have a really wide aperture, and I'm pretty sure this should be in millimeters. This is from someone else. I'm pretty sure this should be in millimeters, not nanometers. If you have a really wide opening, you get very narrow spots. If you have a very narrow opening, you get wide spots. And there's a trend. As the opening gets narrower, the spots get wider and farther apart. And so those are the phenomena that we want to understand today. Okay, so we're going to consider this case. We're going to say that we have a slit, its width is A, and we're just going to add up the fields from each point on the slit. All right, now when we do that, when we add up all the possible points over a wide range, instead of doing a sum, we're doing an integral. And if we're going to figure out the different distances, well, we need a reference point. So we're going to say that R0 is the length of the center path. And then some other path will take a distance R0 plus or minus delta R. And this delta R, this path difference, well, remember these two paths are almost parallel to each other. I've drawn this close because we kind of have to, but in fact, these two paths are almost parallel to each other. So this line here is perpendicular to both paths, which means that, that we have a little right triangle here. And the hypotenuse of that right triangle is y. It's the distance from the center point on the aperture. I use slit and aperture interchangeably. Slit is the geometry. It's just a little dash cut in the screen. And aperture means opening. It comes from the same root word as abierto in Spanish. So it's an aperture is any opening that light can get through. Anyway, y, the distance from the center point on the aperture to the point we're looking at right now, is the hypotenuse of this right triangle. And if this is theta, then this little angle here, this angle here in this little region that's hard to draw, is 90 minus theta. So this is theta. So delta R is opposite theta. And if y is the hypotenuse, then the opposite is going to be y sine theta. All right, so we have to do the integral of e to the ikr over r. And let's see here. R is R0 minus delta R. It's minus because the way I've drawn it, if y is positive, y sine theta is positive, but this path up here is obviously shorter than this path down here. So it's going to be minus delta R. And then we've got a 1 over R, and we have to figure out what R is. Well, let's see. The distance from the aperture to the detector is L, and that's R0 cosine theta. So R0 is L over cosine theta. And if we invert it to get 1 over R0, we've got cosine theta over L. So this is the integral we have to do. Any questions on how or why I set it up that way? Anyone? Going once, going twice. All right. So we can pull out the things that don't depend on y because we're integrating over y. We're summing up the fields from points with different y coordinates. We're going to get cosine theta over L out front and e to the ikr naught out front. And then we've got this integral that looks messy, but actually is related to something very simple. E to the minus iky sine theta. So u is minus ik sine theta y. We're going to do a u substitution. So y is u over minus ik sine theta. So du is minus ik sine theta dy, and dy is du over all that. So we plug all of that mess in here. And now we've just got the integral of e to the u. And the integral of e to the u is just e to the u. So we plug all that in, and we get this expression here. We get e to the minus I, whole bunch of stuff, minus e to the plus I, whole bunch of stuff over some of that stuff. Now that looks like a mess, but we're going to multiply the top and bottom by a over 2. And when we do that, and we're also going to multiply by a minus 1. And when we do that, we get something that looks a lot like a sine. We've got e to the I something minus e to the minus I something over 2I. So we've got sine of Ka sine theta over 2 divided by Ka sine theta over 2. And again, I know it looks like a mess because there's a whole bunch of symbols on the page, and a lot of people get uncomfortable with it, and they start trying to skip steps in the algebra. They want to cancel terms in the denominator with stuff that's inside the sine function. You don't get to do that. Some people want to replace sine theta with theta. That's something that you can only do if theta is small, if you know in advance that theta is small. And even then, it's only approximate. We're not going to be approximate right now. We're going to be as exact as we can be. So to work with an expression like this, if you have to plug it in on the homework, first you have to compute sine theta. You don't get to do something else. You have to compute sine theta. Then you multiply by Ka over 2. Then you take the sine of all that. Then you divide by Ka over 2 sine theta. And this is a new function. It's called the sinc function. Sinc of x is sine x over x. The last time you saw it was probably in calculus. You needed to take the limit of sine delta x over delta x as delta x goes to 0 so that you could calculate derivatives. And then your math professor probably dropped it. But it actually shows up all the time in optics and signal processing. So it's worth saying a little bit about that function and how it works, because many of you, whether you know it or not, are going to eventually have to do some self-teaching in signal processing. It's not a class that you usually take as a physics major, but you're going to get into a science career, and, well, if your experiments or calculations are going well, whatever it is that you were studying, you're going to eventually have to acquire or send some signals. And if you want to send slow signals or send signals using technology someone else has already worked out and you're comfortably within the limits, you don't have to worry about it. But if you want to do something on the edge of performance, the highest speed that's currently feasible with whatever tech you're using, then you have to start thinking about issues of bandwidth. So digital signals are just zeros and ones. And the one, well, a one is either a pulse of light that's on for a certain time interval or a voltage that's on for a certain time interval. And people wind up doing these integrals with that all the time. They multiply this signal by e to the I omega t. They're doing something called a Fourier Transform to break that signal down into different frequencies, to take this square wave, is what they call it, and break it down into a combination of sines and cosines. And they have to do integrals like this. And so they keep getting stuff that looks like that. And there's some stuff to multiply through. But when you do that integral and you multiply some stuff through and simplify it, you get a complex exponential multiplied by the time interval, multiplied by a sinc function. And here's a graph of the sinc function. And you should notice that it has a 0 when the input to the function equals pi. Any questions on that? This function shows up so much that Mathematica has it built in. If I want to compute sine of Ka over 2 sine theta, I don't have to keep on typing that out. If I want to compute sinc of that, I don't have to type out sine of Ka over 2 sine theta divided by sine of Ka, divided by Ka over 2 sine theta, excuse me. I can just go into Mathematica and have it work with something called a sinc function. So you'll notice in this Mathematica file, which I posted yesterday, I define all of these intensity profiles in terms of a sinc function. And great, why isn't Mathematica working out? Because I didn't hit Shift Enter to tell it to run that. All right, so I can take the expression that we had in our notes, which was all of this, and I can square it to get the intensity. And when I square it to get the intensity, I just create a function in Mathematica that computes all of that. And then I can play with the slit width, and I can see how changing the width of the slit, if I fix the wavelength, so I'm fixing K, and I just play with A, you can see how as I increase the slit width, you see how this gets narrower and narrower. This is just like things we've seen before, where when we were dealing with 2 points, we found that if the points were really far apart, the fringes on the screen were really close to each other. And if the points were really close to each other, the fringes on the screen were spread out. And maybe I should change this so that I'm doing it in degrees instead of radians. I know that you have more intuition for degrees than radians. Oh, because I multiplied, but I did my conversion wrong. All right, so you can see how it spreads out over that range. So if we go into our notes and we look at this function, we see that we get a 0 over here if the input to the sinc function, k over 2 sine theta, is an integer multiple of pi. All right? So let's work with that. K over 2 sine theta is 2 pi over lambda times a over 2. Well, the 2's cancel. And that's got to be an integer multiple of pi. So we get that sine theta equals m lambda over a. Now, what did we find when we looked at that experiment? What did the people doing the experiment find for how the width of the peak depended on wavelength and slit size? Anyone recall something from a few slides ago? If we go back to a few slides ago, we find that when we increased the wavelength, when we went from green to red, the spots got farther apart. And sure enough here, the position of this first peak is at an angle whose sine is proportional to lambda. Same for the second peak, same for the third, and so forth. Sorry, not peak, node. But the spacing of the nodes is also the spacing of the peaks. Also, the angle at which this first node and second node and third node and so forth occur, those angles, well, their sines are inversely proportional to the slit width A. So this matches up with the experiment. We have a calculation whose qualitative features match up with the experiment. If we wanted to get to the quantitative features, I'd have to go beyond saying, hey, bright spot here, 0 there, bright spot here, 0 there, and say, well, how rapidly does this decay from bright to 0? How much less bright is this one relative to that one? I'd have to get a lot more quantitative. And we don't have a graph of the intensity that they measured. This is just a schematic here. But at the very least, we can say that the qualitative features are the same. And let's verify that in Mathematica. Well, why? I thought, did I close it? I didn't want to open the second one. Oh, okay, go there. And again, we see that. Now, let's fix the slit width. Let's look at the case of 2. And we see that in the case of 2, if I change the range, so this goes from minus 50 to 50. I get my first node at about 15. All right, and then if I change the wavelength from 500 nanometers or 0.5 microns to 700 nanometers or 0.7 microns, I get that the first node is more like 20 degrees, which is in good qualitative and quantitative agreement because I multiplied the wavelength by 1.4. Going from 500 to 700 nanometers means multiplying by 1.4. And if I take 15 degrees and multiply by 1.4, I get 21 degrees. And all of this that I was doing here was just approximate anyway. I didn't read this with really high precision. So we're getting quantitative agreement. So we can have some confidence in our results so far. Any questions? Anyone? This is all perfectly clear. This is as clear as shot glass covered with an anti-reflection coating. I was actually just arguing on Facebook with a friend of mine who used to work as shot glass before I went on the class. He's a good guy, even if I was arguing with him. No questions. Okay, so then let's talk about why these effects aren't visible in daily life. Well, the first zero happens when sine theta is lambda over a. Let's say our aperture is 1 millimeter. Then our first zero will happen at an angle whose sine is 5 times 10 to the minus 7 meters. That's about the middle of the visible range, give or take. Divided by 10 to the minus 3 meters. So the sine will be 5 times 10 to the negative 4. And if you do the math, that works out to be 0.03 degrees. That is a minuscule angle. To put this in perspective, that would be like looking at a person who's 1 kilometer away. And the width of their chest would probably be, you know, depending on how big and everything they are, but the width of a human torso is roughly 0.5 meter, give or take. And so that would be the size of a human torso at 1 kilometer. That is a really small angular size. At 1 kilometer, you could tell that there's someone there. You couldn't make out any details. So if you've got this smudged out blur of that angular size, no one's going to be able to tell that it was anything other than a perfectly normal shadow. All right. If there are no questions on that, are you sure there are no questions? This is the time to ask. Yeah, Ben.
I'm not sure. How did you know that was the first zero?
How do I know that this is the first zero?
Yeah.
Well, because I'm trying to figure out when is sine of all this mess divided by all this mess equals 0, okay? And the sine function is 0 when its inputs are 0, pi, 2 pi, etc. But if the input to sine, the input to the sinc function is 0, remember the sinc is not just the sine of all this mess, it's the sine of all this mess divided by this mess. And when the input is 0, I've got sine 0 over 0, which is 1. Or the limit is x goes to 0 of sine x over x is 1. So this can't be a 0. So then I ask, well, when else could the input be 0? And the answer is it could be 0 whenever k over 2 sine theta is pi or 2 pi or 3 pi. And the first one, the smallest value of sine theta, would be when this thing here is just pi. So I take all of this, I set it equal to pi, I solve for sine theta. Make sense?
Yeah.
Other questions? Going once. Going twice, 3 times. Sold. Okay. So that's a one-dimensional aperture. The math of a one-dimensional aperture is pretty easy because we've already worked out what that path difference is. It's always K, it's always D sine theta or A sine theta or Y sine theta. It's always some vertical distance, the distance between whatever source you're looking at, whatever your reference is or whatever your other source is, multiplied by sine theta. But in 2D, everything is much more complicated. So let's say we've got a transparent square here, and everything around it is opaque. I know I didn't draw it that way, but I'm not an artist. So we got this transparent square here. This is all opaque. We'll take the center of the square and the center of the detector to be our references. We're going to look at some point that's off-center. And this point that's off-center, we're going to call it point A, and it's at coordinates little x, little y. And on the detector, this other off-center point, which is not necessarily the mirror image of this point. It's not like it's necessarily off at the same angle, the same distance. It could be anywhere on here. That's at big X, big Y. And it's important that point A does not have to necessarily match up with point B, because point B is not just getting light from point A. Point B is getting light from everywhere. It's getting light from here and here and here, everywhere on there, all right? And so because point B is getting light from everywhere on there, we need to be able to calculate the distance from point B to anywhere. And we need to figure out what's the difference between the distance from point B to here or wherever, and the reference distance to the center of the screen. So let's set up some geometry. L is the distance from the center of the screen, the rectangular slit, to the center of the detector. And shoot, I did this wrong. I wanted Y to go from minus A over 2 to A over 2, and X to go from minus B over 2 to B over 2. But right now that doesn't matter. We'll deal with it at the end. Then big R is going to be our reference distance. It's going to be the distance from the center of the detector, sorry, the center of the aperture to wherever we're currently looking on our detector. If I want to find the signal here, the reference distance will be from here to the center of the aperture. And we'll define big R so that little r is big R plus delta R. So if I'm looking at some other point, point A, well, the distance from point A to my point B on the detector is little r, and that's big R plus this. So big R is going to be, just by the Pythagorean theorem, L squared plus X squared plus Y squared. That's the Pythagorean theorem in 3D instead of 2D. And to anticipate what's to come where we start doing Taylor series, we're going to assume that L is big and big X and big Y are small. They're probably bigger than little x and little y, but still, they're small compared to L. So I'm going to factor out this L. I'm going to divide everything in here by L squared. So I divide L squared by L squared and I get 1. I divide X squared plus Y squared by L squared and I get that. And then I'd factor, then I take the square root, and I'm left with this expression. And little r, again, by the Pythagorean theorem in 3D, is going to be the square root of L squared plus the difference in X values squared plus the difference in Y values squared. And in anticipation of what's to come, I again factor out the L. And then we start making approximations. We assume that little x is much less than big X and much less than L. So we don't necessarily want to drop little x entirely. If we drop little x entirely, then we won't have it anywhere in the calculation. But we want to only keep the largest terms that involve little x. And I know that this is kind of a delicate juggling act, but the way to think of it is you've got small terms and then you've got even smaller terms. And if you drop everything, any small term, well, then you lose all of the variables, so you lose how things depend on those variables. If you keep everything, you get something that's impossible to solve. So we follow a middle ground. We only keep the least small, or the biggest of the small, however you want to think of it. We say we got a bunch of terms, All of them are small, but some of them are even smaller still. We'll drop the really small and keep the just kind of small. And all the same things apply to the y's. So I'm going to say that r is roughly equal to, after we drop all the little x squared and the little y squared, 1 plus all this, plus, and this is supposed to be a 2 times little x, this is supposed to be a minus 2 here, little x, big X, little y, big Y, all over L squared. Then the next thing we do is we assume that all of this stuff here is much less than 1, okay? And if we assume that it's all much less than 1, then we get to use a Taylor series. You get to use the fact that 1 plus alpha to the n is roughly 1 plus alpha n if alpha is small. And we're taking a square root. So n is a half, all right? And alpha is just all of this stuff here that I forgot to put in. So r is going to be roughly 1 plus 1/2 of all this mess. And big R is going to be, and it's all multiplied by L, and big R is going to be L times 1 plus 1/2 multiplied by this somewhat smaller mess. Now here's the great thing. 1 plus 1/2 times this smaller mess, that shows up in our formula for little r. So what we know immediately is that little r is big R plus some other stuff. And that's exactly what we said before. We said that little r is going to be defined so that it's big R plus a difference. This is exact. You can say that any variable is equal to some other variable plus the difference, okay? You could say that, you know, the difference between my income is just equal to a millionaire's income minus a very large number. That is by definition mathematically true, all right? So when we do all that, we're left with little r equals big R minus L times all of this stuff. And there was a 2 in all of these terms. And that cancels out the 1/2 that came from the Taylor series for square root. And there's an L which cancels one of the factors of L in the denominator. And we're left with this. This expression is certainly a lot simpler than this thing. But it's more than just something that's simple enough to do math with. It's something that we can give a physical or geometrical interpretation to. Because we're going to be taking e to the I k r, which is e to the I k big R minus I k delta r. So we're going to keep, when we take k delta r, we're going to have k times big X over L. We're also going to have k times big Y over L. And we can interpret these things, all right? If we think of the k vector as going from our aperture to a point on our detector, then we can interpret the k vector geometrically, and we can say that the k vector is in the same direction as r, the vector from the center of the screen, center of the aperture to a point on the detector. And kx would just be opposite to this here, and ky would be opposite to that. And the ratio of kx to the length of k would be the same as the ratio of big X to this distance. So that's kx over k is going to be big X over L. Ky over k is going to be big Y over L. You might be saying why L and not R? Well, now we're kind of assuming small angles. Oops. So the end result of that is that k times big X over L is just the x component of the k vector. And k times big Y over L is the y component of the k vector. And here's one other important thing to notice. I haven't said a single word yet about this aperture being a square. I mean, I said it at the beginning, but then I never used that fact. Nowhere in any of these assumptions, nowhere in any of this work did I need to assume that the aperture was a square? I didn't even assume that the detector was a square. I just assumed that we got a point big X and big Y somewhere in the detector plane, and the point little x and little y somewhere in the aperture. I never said anything about squares or circles. Never said anything about the shape. Squares, rectangles, whatever. Never assumed any of it. So I've got this integral. I've got that the electric field will be proportional to this thing, which is just a constant, multiplied by this integral over the aperture of e to the minus I, x component of k multiplied by x, e to the minus I, y component of k multiplied by y. And for this shape, we get something very, very simple. But we just get the product of two integrals because we've got an integrand that's we've got a double integral, but our integrand is the product of two functions, one of which only depends on x, one of which only depends on y. And so because of that, we've got something very simple here. We get the product of two sinc functions. Now let's show those in Mathematica. If we go to the second file that I posted, I define the rectangle intensity profile to be the product of two sinc functions. That gives you an electric field. Then I square it to get an intensity. I'm going to say that the vertical height is 2. So we're going to fix that. And I'm going to say that the wavelength of light is 532 nanometers, which is a typical green laser pointer. Those are fun laser pointers to play with because, first of all, they're very bright. Those are very highly efficient laser pointers. Also, green is an excellent wavelength for exciting a lot of fluorescent dyes. Before I realized that I should really be doing calculations, I spent a lot of time playing with green lasers and fluorescent dyes in grad school. I have a whole bunch of stories that, much like American Pie and this one time at band camp, begin with, and then this one time at grad school. So if we deal with my favorite laser wavelength, we get this. And what you should notice is that this is, first of all, a rectangular pattern. And as I change the horizontal size, the shape of the pattern changes. And it always looks pretty psychedelic. That's one of the fun things about playing with these diffraction patterns. Diffraction just means light spreading out and interfering with other light that's spread out from other points. The diffraction patterns tend to look very psychedelic. They look even more psychedelic than when I was playing with the virtual background for my face in Zoom. Because you get all of these repeating bright colors. And let's see if I can, no, I can't do magnify. Oh, let's play with the magnification here. All right, that's one thing you should notice. You should notice that we've got these bright colors. You should notice that we've got this pattern of spots. We've got spots both vertically and horizontally. Here's another thing you should notice. If I make the horizontal width of the slit really small, so I say that B, the width of the slit along the x direction is 0.5, and A, the width of the slit along the vertical direction is 2, that means that I've got something that's oriented vertically. And when it's oriented vertically, the slit, the aperture is oriented vertically. But the diffraction pattern is oriented horizontally. And conversely, when I change it around like this, so that now the horizontal width of the slit is huge compared to the vertical width. Now I've got something that's oriented horizontally, and the diffraction pattern is definitely more vertical. And in between, if I make B roughly 2, I don't know if I'll get exactly 2 on here, now you get something that's even. Anybody guess why that is before we go into the notes? Anyone? Anyone? Bueller? Bueller? All right. So we get a 0 along the horizontal direction. We got that's dependence on the x component of the k vector is kx multiplied by b. All right. So we get a 0 when kx multiplied by b over 2. So if I switch to my tablet, so now hang on, I'm going to switch so that I can write. I'm going to share this one, share my screen on my tablet, and then go into OneNote. All right, we've got sinc kxb over 2, sinc kya over 2. And that's equal to 0 if kxb over 2 equals pi times an integer, or kya over 2 equals pi times another integer, which I'm going to call n. And yes, I'm aware that n is also a refractive index, but some symbols inevitably get reused. So if I work with this, I've got that 2 pi b over 2 lambda sine theta x equals pi times an integer. Well, didn't want that. Cancel, cancel, cancel. So I get that sine of theta x equals m lambda over b. All right. And what do I mean by theta x? I mean that if I've got my source here, this is B, this is A. All right, so this is going to be, if I project my K vector, all right, so I've got that this is KZ, this is KX, and this is KY, then this angle here would be theta x. And this angle here would be theta y. All right. So I get a 0 whenever sine of theta x is m lambda over b, or if I went through all of the same reasoning, when sine of theta y is n lambda over a, because I would just do 2 pi sine theta y a over 2 lambda equals pi, and I keep touching that. I'm holding my stylus the wrong way. Spent decades building up how to work with chalk and whiteboard markers. And then a virus takes away all of those skills. All right, so we're left with sine theta y. The 2's, that's a separate process there. The 2's cancel, the pi's cancel. We're left with sine theta y equals lambda over a. All right, so if a is small, then the peaks and nodes along the y direction are close, are far apart, sorry, because a is in a denominator. Well, that thing out of the way. Large B peaks and nodes along X are far apart. So that explains what we see in Mathematica. Any questions right now? All right, I'm going to share this again. Go back to Mathematica. Well, wait, I've already got that. I just want. All right. So again, we see the confirmation of what we saw before, that when B is large, then we get that everything is very closely spaced along the horizontal axis. But when A, you know what? I'm rescaling all of this every time I do that. I'm going to take out those factors of A and B. And then maybe things will be a little bit more apparent. Okay, what happened was that because I had factors of A and B in there before, it seemed like a good idea at the time. All right, I changed the contrast essentially. Anyway, when B is large, you get a very narrow pattern. It's most noticeable, so it's very narrow horizontally, noticeable variation in the vertical axis. When B is small, you get a very wide pattern, and its most noticeable variation is along the horizontal axis. Any questions? Yes, Ben.
So when we're talking about if B is large or small, that's when the slit or the aperture is larger or smaller or kind of like taller or
You could think of B as how wide it is along the X direction, and A is how long it is along the vertical direction. Okay, so let me switch back to my other device and go into OneNote. Okay, so this would be a case of small b, large A, and then we're going to get a diffraction pattern that looks mostly like this. Conversely, here we have small a, large B, here's our diffraction pattern. And this is a general phenomenon we're going to see over and over again with diffraction, that when you have something that's large, some feature that's large on the object, like something that's very wide in the horizontal direction, the diffraction pattern is very narrow in the horizontal direction. If you have something that's very long in the vertical direction, the diffraction pattern is very narrow in the vertical direction. And conversely, if something is narrow in the vertical direction, you get a diffraction pattern that's very wide in the vertical direction. Which is why if you go further into diffraction theory, you will often hear people start saying that diffraction patterns exist in reciprocal space, or they involve reciprocal vectors. And that doesn't literally mean putting vectors into the denominators of expressions. If you try to divide by a vector, I will mark you wrong, I will cry. But it means that they're working in a mathematical formalism where all of the lengths get inverted, all right? And so if you read a book on X-ray crystallography, which is used all the time in materials science, solid state physics, even biophysics for figuring out the structures of proteins, people will talk largely about reciprocal vectors, reciprocal space. They'll talk about the diffraction pattern, showing you how things are built up in reciprocal space. And then there are some mathematical procedures that you follow to go from reciprocal space to real space. And it's more than just taking 1 over something. It's a little more complicated than that. Other questions? Ben, your hand's still up. Do you have another question?
I do, but it's about kind of the beginning of the lecture, so I would just wait until
No,
you're
that's fine.
actually
You're
done.
probably not the only one to have a question about the beginning of the lecture. So let's go back to the beginning of the lecture. We've got a few minutes. All right, what's your question?
Why is m equaling 1, 2, and 3 on that first slide that you were just on, where the interference is destructive?
Because it was mathematically easier to find the destructive interference. We could do the constructive interference, but then the constructive interference, a sine is 1 when the input is pi over 2. It's -1, which doesn't sound like constructive interference, but remember that the intensity is the square of the field. So if the field was a large negative number, the intensity would be a large positive number. So you'd get pi over 2, 3 pi over 2, 5 pi over 2. It's just slightly less convenient to work with. So by convention, we're following something called the principle of least action here. We're just taking the easy route. So if you hear someone talking about a diffraction pattern and they start saying m equal 1, m equal 2, just go ahead and ask, are you counting is m counting the zeros or the maxima? That's perfectly fine.
Also, can you explain the reason behind that first integral that you set up? I was taking notes, so I didn't ask.
This integral?
Yeah.
Okay. The field, if I've got waves spreading out from a point right here, the field of a wave spreading out from a point is e to the ikr over r. But I'm not just taking the field from this point or this point or this point. I'm taking all of those fields and adding them. And an integral is adding up fields from an infinite number of infinitesimally spaced points. At this point, I'm going to shut things down so that those who have something else to do, this class was only scheduled till 10:50. Those who have something else to do can do it. If other people want to ask questions, I am going to shut down Zoom just so that this has a finite. Actually, you know what? I'll stay on Zoom, and anybody who wants to hear the Q&A can hear it when we go on YouTube. But anybody who wants to log off, feel free to do so. I'll stay on Zoom for a few minutes for those who have questions. The next hour is an office hour. I'm not in my office, so you can't call my office phone, but you can send me an email, and if necessary, we'll set up another Zoom chat. And remember that there's a problem set due Wednesday, and I will be available to take questions on it. Have a good day. All right, since nobody's asking questions, I'm going to end this meeting.